Hello everyone, I'm Meurice from UC Louvain in Belgium, and I am very pleased to present you some of my research outcomes. Actually, the work I am about to present you is part of my PhD thesis that is geared towards the development of two-dimensional finite volume models able to simulate the morphodynamics of rivers subject to fast transient flows. However, here I will only focus on bedload models that use an HLLC solver to compute the fluxes at the interfaces between cells. Two models will be discussed and applied to several test cases that highlight their potential but their limitations as well. So first of all, I will present you the hypotheses and equations that lead to the two models considered here and will discuss their differences. After that, I will show you some results that were obtained for 3 test cases for which experimental data also exist. And finally, I will draw some conclusions and deliver some take-home messages. Okay, so as previously mentioned, the models that I am about to discuss are two-dimensional finite volume models which solve the shallow water equations for one single layer of water with a velocity u and depth h that is lying upon another finite layer of sediment for which the Exner equation only will be solved. Hence, the movement of sediment is only due to bedload and will depend on the closure equation for the solid discharge Qs. Even though a large number of formulae exist for that, I only use the Mayer, Peter, and Mueller closure formulation though. So altogether there are 4 equations since there is a momentum equation in both the x and the y direction, and hence 4 state variables, which are the depth h, the velocity components u and v, and the bed level zb. We can then sum up the variables, the fluxes in both directions, and the source terms in 4 vectors, u, f, G and S respectively, and end up with a global formulation for the two-dimensional problem. Nevertheless, to use these models on unstructured grids, I applied a rotation matrix to transform the problem from 2D to 1D locally at each interface, and also to better balance the slope source terms, I passed it into the left term of the equation to include it into the flux resolutions. So the right term then only consists in the friction source term. So as you may know, finite volumes are based on the transfer of mass and momentum from one cell to another through their interfaces. To compute the right amount that needs to be transferred, several solvers can be used, but this study only focused on the HLLC solver, which is very widely used and easy to implement as well. With the solver, the flux at the interface F star will depend on the most extreme characteristics of the flow, lambda plus and lambda minus, on the fluxes computed for the cells on either side of the interfaces FL and F right, and finally on the state variables of these same cells UR and U left. Okay, so both models rely on the same equations and the same flux solver, but the difference lies in the coupling. For the coupled model, the shallow water equations are solved together with the Exner equation so that we end up with vectors and matrices of dimensions 4×1 and 4×4 respectively. And consequently, the eigenvalues of the problem will not be really straightforward, but will depend on the solid discharge formulation, at least for 2 of them. Furthermore, the application of the HLLC flux on the last equation concerning the bed level will be kind of problematic because of its last term here. You can indeed see that if the bed is not perfectly plane, we will continuously have some transport, even though the transport capacity is not high enough. To solve this problem, I applied a weakly coupling of Carmelo-Ruiz on this HLLC-based model. It actually consists in solving separately the shallow water equations and the Exner one. We then cannot use the HLLC flux for the bed level equation since we have no characteristic that is linked to that variable anymore. Instead, we can use a full upwind scheme that is based on a numeric characteristic lambda s that is obtained by inverting the Exner equation and whose sign will indicate the cell from which the solid flux must come from. In this way, we no longer should see any excessive diffusion effect. To validate these models, I first applied them to a one-dimensional Dambreck test case for which experimental data were collected by Spinwin and Zek in 2007. Back then they were able to determine the limits of a movable bed layer, here represented by ZB low, black, and ZB up in green. However, the bedload models considered here are not able to determine such a layer depth. Instead, they rather deliver an estimation of the mean bed level of each cell. First of all, the authors used sand as bed material, leading to a slight transport, only that both models were able to capture satisfactorily. You can indeed see on the left pictures that both models deliver bed levels that are comprised between the black and the green curves. After that, they replaced the sand by PVC pellets, which are way lighter and whose particles have a larger diameter, leading to much more transport. As you can see, the movable bed layer is now much larger. The coupled model does not look to be able to follow such an important transport and actually becomes unstable with some distinctive bumps at 0.5 seconds and 1.25 seconds, which is not the case of the weakly coupled model that remains coherent. After this first test, I applied the models to a two-dimensional dam break test case on an erodible flat plane that was originally reproduced and discussed by my supervisor and several other authors in 2012. As you can see, both models were able to reproduce the score near the gate and the arrow-like deposition pattern, but the weakly coupled model was far more accurate. The coupled model results indeed look kind of blurred, which is due to the excessive diffusion of that model that we wanted to solve with the weakly coupled model. Besides, the profiles taken along that red line here clearly show that the weakly coupled model already gets really good results for a low resolution R, and that the gain is maybe not worth the computational effort, whereas for the coupled model we clearly see an improvement of the model with a finer resolution. So not only is the coupled model less accurate because too diffusive, but it is also more mesh sensitive. Finally, both models were applied to another two-dimensional dam break, but in a channel with a 90-degree bend, as you can see on this illustration. Here we will focus on the zone framed in red, where most of the transport takes place. You can already notice that both models did not perform very well here. They were indeed able to determine the maximum deposition and erosion zones, but they clearly underestimated their amplitude, especially the coupled model, once again because of its diffusive character. I have actually led some experiments lately, and they proved that this weak performance of both models could mainly be attributed to their inability to cope with secondary currents and sediment inertia. And although the weakly coupled model much better predicted the slope of the bed close to the end of the flume, as you can see on both profiles, it also overestimated by far the erosion near the inner corner of the bend. It is actually the only place where the coupled model gives better results than the weakly coupled model, and I assume that diffusion here kind of helps to balance the sensitivity of the model to flows with an enormous transport capacity. So, what you can remember from this presentation is that bedload models can be a very nice tool to quickly estimate the transport of sediment when mainly happening near the bed. Nevertheless, we saw that the coupled model was based on a too diffusive bed material flux and that decoupling the shallow water equations from the Exner one could help fix this problem. The application of these two models showed that the weakly coupled model gave more stable results in case of large sediment transport, that its results were less diffuse of course and consequently more accurate, as well as less mesh sensitive. Nevertheless, some diffusion could sometimes be helpful to smoothen the bed when the transport capacity computed by the model gets very large. Without this, we can indeed get unrealistic bed level estimations if non-capacity module is activated. And of course, just like the bedload model, the weakly coupled model does not handle sediment inertia properly enough for channels with complex geometries. In conclusion, I think that two-dimensional bedload models using the HLLC flux should follow the weakly coupling modeling approach, but when the geometry of the river or the channels becomes complex, or when suspension also comes into consideration, more complex models coping with sediment inertia, like two layers or two phases models, maybe constitute a more interesting alternative. Alright, so I deeply thank you for your attention, and if you have any question, please feel free to contact me through my email address that you can find on this slide. Wish you a very good day and a nice conference as well.